Welcome to the Secret Code Maker. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are going to learn about something really cool called HKDF, but I am going to explain it in a way that is super easy to understand. Think of HKDF as a magical machine that takes a secret password and turns it into many different secret codes. Just like how a juice machine takes one orange and makes a whole glass of orange juice. Imagine you and your best friend want to send secret messages to each other. You have one secret password that only you two know. But what if you want to send messages using different secret codes for different types of messages? Maybe one code for homework answers, another code for surprise party plans, and another for video game strategies. That is exactly what HKDF does. It takes your one secret password and creates many different secret codes from it. The name HKDF sounds complicated, but it simply means a way to make secret keys from one secret. Think of it like a magic recipe. You start with some secret ingredients, mix them in a special way, and you can derive many different secret codes. Each code is completely different from the others, so even if someone discovers one code, they cannot discover the others. We are going to use real numbers in this presentation so you can see exactly how it works. We will use actual examples that show you the real inputs and outputs. By the end, you will understand how computers keep your messages safe using this cool trick. What is a hash function, the blender? Before we can understand our secret code maker, we need to learn about something called a hash function. I like to think of a hash function as a magical blender. When you put ingredients into a blender and turn it on, you get a smoothie. The smoothie looks completely different from the ingredients you put in, and you cannot unblend it back into the original ingredients. That is exactly what a hash function does with text and data. Let me show you with a real example using a simple hash function. We will use the word apple. When computers hash this word, they look at each letter, give it a number value, add them up, multiply them, and perform special math operations. The letter A might be worth 1, P is worth 16, and so on. After all the math magic, the word apple might turn into a long number. Here is what makes hash functions so cool. If we change even one tiny thing about our input, we get a completely different output. If we use apple with a capital A instead of apple with a lowercase a, we get a totally different output. Just changing one letter from lowercase to uppercase generated a dramatically different result. This is super important for keeping secrets safe. Another amazing thing about hash functions is that they always give you the same answer for the same input. If you hash the word apple today, you get a consistent numerical output. If you hash apple tomorrow, you still get that consistent numerical output. If you hash apple repeatedly, you always get the same number. This is called being deterministic, which is just a fancy word for always getting the same answer. The last cool thing about hash functions is that you cannot work backwards. If I tell you the output, which is a very large number, you cannot figure out that the input was apple. You would have to try every possible word until you found one that gives you that exact number. This would take years and years. This one-way property is what makes hash functions perfect for creating secret codes that nobody can crack. HMAC, adding a secret key to the blender. Now we are going to learn about HMAC, which is like our hash function blender but with a secret lock on it. Remember how our hash function could take the word apple and turn it into a big number? Well, HMAC does something even cooler. It takes a secret key that only you know, and it mixes that secret key with your message before hashing it. This way, only someone who knows the secret key can make the same hashed result. Let me show you with a real example. Let's say our secret key is the word dog, and our message is the word cat. HMAC does not simply combine these. It performs a much more clever operation. First, It takes the secret key dog and pads it with extra characters to make it exactly 64 characters long. So dog becomes dog followed by 61 spaces or zeros. Then HMAC does a special XOR operation. XOR is like a secret mixer that flips bits. Imagine each letter is actually a pattern of ones and zeros. XOR mixes these patterns in a special way. HMAC takes our padded key and XORs it with a special pattern called IPAD, which is the number 36 repeated over and over. This creates a new mixed key. Then it adds our message cat to this mixed key and hashes everything together. This gives us an intermediate result. But HMAC does not stop there. It takes the original secret key dog again, pads it to 64 characters, and XORs it with a different pattern called OPAD, which is the number 92 repeated over and over. This creates another mixed key. Then it takes this second mixed key and combines it with our intermediate result from before, and hashes that. The final output might be a big number. This is our HMAC output. Why do we hash twice with two different patterns? Think about it like making a super secure lock. One lock is good, but two locks are even better. The double hashing with different patterns makes it super hard for anyone to figure out your secret key even if they see the final result. If someone sees, they cannot work backwards to figure out that your secret key was dog and your message was cat. This double protection is what makes HMAC so secure and perfect for HKDF. HKDF Extract making strong secret sauce. Now we are ready to learn about the first part of our secret codemaker machine. It is called the extract part, and I like to think of it as making a super strong secret sauce. Imagine you have some ingredients that might not be perfect. Maybe you have some orange juice, but it is a little bit watery. The extract part is like concentrating that juice to make it strong and perfect. Let me show you with a real example how extract works. Let us say you and your friend did a Diffie-Hellman key exchange, which is a way to agree on a secret over the internet, and you both ended up with the shared secret word sunshine. This will be our input key material or IKM. Now you also need something called salt. Salt is just a random value that makes your secret sauce even stronger. Let us use the word random 123 for our salt. The extract part uses HMAC that we just learned about. It takes your salt, random 123, and uses it as the secret key for HMAC. Then, it takes your input key material, sunshine, and uses it as the message. So, we are doing HMAC with key equals random 123, and message equals sunshine. Remember how HMAC works with the double hashing and XOR operations we learned about in the previous slide. Let me walk through what happens. First, HMAC takes random 123 and pads it to 64 characters. Then it XORs this with IPAD, which is 36 repeated. This creates a mixed key. It combines this mixed key with sunshine and hashes them together. This gives us an intermediate value. Then it takes random 123 again, pads it, XORs with OPAD, which is 92 repeated, and combines that with the intermediate value and hashes again. The final result might be a long string of letters and numbers like beginning with 5F and ending with 1A. This is our PRK, which stands for pseudo-random key, but we can just call it our super secret sauce. Now we have our super secret sauce, which is beginning with 5F ending with 1A. This sauce is perfect for making secret codes because it is both super strong and super random. Even though we started with simple words like random 123 and sunshine, after all that HMAC processing with padding and XOR and double hashing, we got beginning with 5F ending with 1A, which looks completely random and has no obvious connection to our original words. This super secret sauce is what we will use in the next step to make all our different secret codes. The magic is that both you and your friend can make this exact same sauce if you both have the same salt and IKM. HKDF Expand, making many secret codes. Now comes the really fun part. We have our super secret sauce, which is beginning with 5F and ending with 1A from the extract step. Now we are going to use the expand part to make many different secret codes from this one sauce. Think of it like having one bottle of concentrated juice and making many different glasses of juice from it. Each glass is unique because we add different flavors to each one. Let me show you how to make the first secret code. We start with our super secret sauce, beginning with 5F ending with 1A. We also need something called info, which serves as a label for what this code is for. Let's say our first code is for encrypting homework messages. Our info then becomes the text encryption key. We also add a counter, which is simply the number 1, to indicate this is the first block we are making. Now we use HMAC again. We use our super secret sauce, beginning with 5F ending with 1A, as the secret key for HMAC for the message. We combine our info encryption key with our counter, 01, in hexadecimal. So, the message to HMAC is encryption key followed by 01. We run this through HMAC with all its padding, XOR, and double hashing, and we might get an output like, beginning with a 7 ending with B4. This is our first derived key, a 32-character secret code, perfect for encryption. But here is where it gets really cool. What if we need a second secret code for authentication instead of encryption? We use the same super secret sauce beginning with 5F ending with 1A, but now our info is auth key instead of encryption key, and our counter is still 01. When we do all the HMAC processing with these new inputs, we might get a completely different output like beginning with 3C ending with 7E, so our authentication code is beginning with 3C ending with 7E. Notice how it is totally different from beginning with a 7 ending with B4 even though we used the same super secret sauce. That is the magic of using different info labels. What if we need even longer keys? Let us say we need 64 characters for a really strong encryption key. We can make a second block. For block 2, the message to HMAC includes the previous block result. So we take beginning with a 7 ending with B4, add our info encryption key, and add counter 02 for the second block. When we HMAC this, we might get beginning with 6F ending with 1F. Now we combine our two blocks together. Beginning with a 7 ending with B4 plus beginning with 6F ending with 1F gives us a 64-character key. This chaining of blocks is what lets HKDF create keys of any length we need. The expand part can make as many secret codes as you need. Each code uses a different info label to make it unique. You might have encryption key, auth key, signing key, and more. Each one produces a completely different code even though they all came from the same super secret sauce. This is why HKDF is so powerful. You start with one shared secret, turn it into super secret sauce with extract, and then make unlimited different codes with expand. Pretty cool, right? Complete HKDF example step by step. Now, let us put everything together and walk through a complete, real example from start to finish. This will help you see how all the pieces we learned about work together. We will start with a shared secret between you and your friend, and end up with multiple different keys you can use for different purposes. This is exactly how computers protect your messages on the internet. Imagine you and your friend Alice want to send secret messages. You do a Diffie-Hellman key exchange over the internet, and you both end up with the shared secret word moonlight. Nobody else knows this word, only you and Alice. You also agree on a salt value, which is the word salty 789. The salt does not need to be secret, but it needs to be the same for both of you. Now you are ready to start HKDF. First comes the extract step. You take your salt salty 789 and use it as the HMAC key. You take your shared secret moonlight and use it as the HMAC message. Remember, HMAC pads the key to 64 characters, then does XOR with IPAD, which is 36 repeated hashes with the message. then XORs the key with OPAD, which is 92 repeated, and hashes again. After all this processing, you get your PRK, which might be beginning with 3F, ending with 3B. This is a 32-character hexadecimal string which represents 16 bytes of super strong random data. Now comes the expand step, where we make multiple keys. Let's say you need 3 different keys. You need an encryption key to scramble your messages. You also need an authentication key to prove the messages came from you. And you need an IV, which stands for initialization vector. This IV is like a starting number for your encryption. Each of these needs to be different, even though they all come from the same PRK. For the encryption key, you use your PRK beginning with 3F ending with 3B as the HMAC key. Your message is the info label message encryption followed by the counter 01. You HMAC this and get output beginning with 8A ending with 4D. This is your encryption key. For the authentication key, you use the same PRK as the HMAC key, but your message is now message auth followed by 01. You HMAC this and get a different output beginning with 2C ending with 3B. This is your authentication key. For the IV, you use the same PRK, but your message is now message IV followed by 01, and you HMAC to get beginning with 5E ending with 7F. Now, you have 3 completely different keys, all derived from your one shared secret, Moonlight. You and Alice can both perform this exact same process, and you will both get the same 3 keys because you both know Moonlight and Salty 789. However, nobody else can figure out these keys, even if they see your messages, because they do not know your shared secret. This is the power of HKDF. One secret becomes many keys in a secure and organized way. Why HKDF is super secure. Now, let's discuss why HKDF is so secure and why computers worldwide use it to protect your information. HKDF is highly robust, and there are several reasons why adversaries cannot break it, even with significant effort. Understanding these security features will help you appreciate this system's clever design. The first reason HKDF is secure is because of the one-way property of hash functions. Remember how we learned that you cannot unblend a smoothie? That is what makes hash functions one-way. If a bad guy sees your final key like beginning with 8A ending with 4D, they cannot work backwards to figure out your PRK or your original shared secret Moonlight. They would have to try every possible combination of words and numbers, which would take longer than the age of the universe even with the fastest computers in the world. The second reason involves the double hashing used in HMAC. By hashing twice with different XOR patterns, HMAC protects against sneaky attacks that rely on single hashing. Even if an attacker knows some of your keys, they cannot use that information to figure out your PRK or to predict what your other keys might be. Each key appears completely random and gives no clues about the others. This is like having a lock that cannot be picked, even if an attacker has X-ray vision. The third reason is the salt in the extract phase. The salt ensures that even if 2 different people use the same password, for example, Moonlight, they will get different PRKs because they use different salts. This prevents something called rainbow table attacks where bad guys build huge databases of pre-computed hashes. With salt, every extraction is unique, and the bad guys cannot prepare their attacks in advance. They have to start from scratch every single time. The fourth reason is the info labels in the expand phase. By using different info labels like message encryption and message auth, we make sure each key is bound to its specific purpose. Even if a bad guy somehow steals your encryption key, they cannot use it as an authentication key because it only works for encryption. The info labels create separation between different uses. This is called domain separation, and it is a super important security principle. The last reason is that HKDF is standardized and tested. Thousands of smart cryptography experts have looked at HKDF and tried to break it, and nobody has found a way. It is used in important systems like when your web browser makes a secure connection to a website using HTTPS. When you see that little lock icon in your browser, HKDF is part of what is protecting you. Knowing that the world's best security experts trust HKDF should make you feel confident that your secrets are safe. Real-world uses of HKDF. HKDF is not just a cool idea we learn about. It is actually used every single day to protect billions of people around the world. Let me tell you about some of the amazing places where HKDF is working behind the scenes to keep your information safe. You have probably used HKDF today without even knowing it. The first significant use of HKDF is in web browsing. When you visit a website that starts with HTTPS, such as when you log into your email or make an online purchase, your computer and the website perform a special handshake called TLS. Part of this handshake uses HKDF to create all the secret keys required to encrypt your messages. Your computer and the website agree on a shared secret using Diffie-Hellman. Then they use HKDF to derive multiple keys from that single secret for encryption, authentication, and other purposes. This happens automatically every time you see that lock icon in your browser. The second use is in messaging apps like WhatsApp, Signal, and iMessage. When you send a message to your friend, these apps use HKDF to create unique encryption keys for each message. They start with a root secret key that you and your friend share, then use HKDF to derive a new key for every single message. This means that even if a bad guy somehow gets the key for one message, they cannot read any of your other messages. Each message is protected by its own unique key thanks to HKDF. The third use is in VPNs, which stands for Virtual Private Networks. A VPN is like a secret tunnel through the internet that keeps your browsing private. When you connect to a VPN, your computer and the VPN server use HKDF to create encryption keys for the tunnel. These keys protect everything you do online from people who might be snooping on your internet connection. Companies use VPNs to let their employees work from home securely, and people use VPNs to protect their privacy when using public Wi-Fi at coffee shops or airports. The fourth use is in password managers. A password manager is an app that remembers all your passwords for different websites, so you do not have to. These apps use HKDF to turn your one master password into many different encryption keys. Each website's password is encrypted with its own unique key derived from your master password using HKDF. This way, if someone breaks into the password manager's database, they cannot read your passwords without knowing your master password, and even then, they have to crack each password separately. The fifth use is in cloud storage like Google Drive, Dropbox, and iCloud. When you upload a file to the cloud, these services use HKDF to create unique encryption keys for each file. Your main account key gets turned into thousands of individual file keys using HKDF. This means that even if someone steals one file key, they cannot decrypt your other files. HKDF makes it possible for cloud companies to give you strong security without having to store millions of separate keys. Pretty amazing that this one technique protects so much of our digital lives. Common mistakes and how to avoid them. Even though HKDF is a great tool, people sometimes make mistakes when using it. Let's discuss some common errors and how to avoid them. Learning from these mistakes will help you use HKDF correctly, especially when writing programs that need to keep secrets safe. The first common mistake is using the same salt and shared secret for different purposes without changing the info label. Remember how we used different info labels like message encryption and message auth? Some people forget to do this, and they use the same inputs for everything. This is bad because you end up with the same keys for different purposes. Imagine using the same key to lock your house, your car, and your bike. If someone steals that one key, they can get into everything. Always use different info labels to make sure each key is unique for its purpose. The second mistake involves reusing salts. The salt is supposed to make each HKDF extraction unique. Some programmers might reuse the same salt repeatedly for different extractions. This is dangerous because it means different shared secrets might produce related keys, which makes it easier for malicious actors to compromise your system. Always generate a new, random salt each time you perform an HKDF extraction. Think of salt as a unique ID for each batch of keys you create. Each batch requires its own ID. The third mistake is using weak shared secrets. HKDF is amazing at turning one secret into many keys, but it cannot make a weak secret strong. If your shared secret is something easy to guess like the word password or the number 1234, then HKDF cannot save you. Bad guys can just try all the common passwords and see which one produces keys that decrypt your messages. Always start with strong shared secrets that are long and random. If you are using passwords, use a password manager to generate random ones that are at least 20 characters long. The fourth mistake is not protecting the PRK properly. Remember that the PRK is your super secret sauce that can make all your keys. Some programs make the mistake of storing the PRK in a file or database where bad guys might find it. If someone steals your PRK, they can make all the same keys you can. The PRK should stay in your computer's memory only while you are using it, and you should erase it from memory as soon as you are done. Never write the PRK to disk and never send it over the internet. The fifth mistake is not using HKDF at all, and trying to create your own system. Some programmers think they can invent something simpler than HKDF. They try to just hash their password a few times to make keys. This is a terrible idea, because they often make security mistakes that expert cryptographers would never make. HKDF has been carefully designed and tested by the world's best security experts. It is always better to use a proven system like HKDF, rather than trying to invent your own. There is a saying in security: do not roll your own crypto. This means, do not create your own cryptography. Instead, use what the experts have built. Summary and key takeaways. We have learned so much about HKDF today. Let me summarize all the important points so you can remember the key ideas. HKDF is a powerful tool that turns one secret into many keys, and now you understand exactly how it works and why it is so important for keeping your information safe on the internet. First, remember that HKDF has two main parts: extract and expand. The extract part takes your shared secret and assault, and uses HMAC to create a strong PRK or super secret sauce. The expand part takes that PRK and uses HMAC again with different info labels to create as many different keys as you need. Each key is completely different and secure, even though they all came from the same PRK. This two-step process is what makes HKDF so powerful and flexible. Second, remember that HKDF builds on hash functions, and HMAC hash functions are like magic blenders that turn any input into a number, and that process cannot be reversed. HMAC adds a secret key to the hash function, so that only people who know the key can make the same hash. HKDF uses HMAC multiple times in clever ways to create secure keys. Understanding these building blocks helps you understand why HKDF is secure. Third, remember that HKDF is used everywhere to protect you online. When you browse websites with HTTPS, send messages on WhatsApp, use a VPN, store files in the cloud, or use a password manager, HKDF is working behind the scenes to keep your information private. Billions of people rely on HKDF every day, and it has been tested and proven secure by the world's best cryptography experts. You can trust that HKDF is doing its job to protect you. Fourth, remember the important details that make HKDF work correctly. Always use different info labels for different purposes. Always use random salts for each extraction. Always start with strong shared secrets. Always protect your PRK and never store it where bad guys might find it. And always use standard implementations of HKDF from trusted libraries instead of trying to build your own version. These best practices ensure that HKDF stays secure. Finally, remember that cryptography is all about keeping secrets safe, and HKDF is one of the most important tools we have. It lets you take one secret and create a whole family of keys, each one perfect for a different job. Whether you are encrypting messages, authenticating users, or protecting files, HKDF gives you the keys you need. Now you understand the magic behind how computers keep your secrets safe. Pretty cool, right? Thank you for your attendance. Please consider subscribing to the channel.